Thanks a lot for coming to my talk today. It's been a long day, I appreciate, but we're getting towards the end now. So my name's Neil Hickey. I work in the compiler team at ARM, working in the MPG, which is the Media Processing Group. So my team's responsible, or the department I work for is responsible for all the compilers that run on our GPUs. So I want to talk to you today about SPIR-V. Some of you may have heard of SPIR-V and Chronos, but if not, I'll introduce it. There's quite a few slides to get through, so I'll go quite quickly, but if there's any questions, feel free to ask me at the end or catch me at the break afterwards. So a quick introduction to Chronos, for those who don't know. So Chronos is a standards body. It's responsible for producing the APIs and the languages for some of the major APIs that run on GPUs. Mainly for OpenGL. They also produce OpenCL standards, OpenGLES as well, and most recently Vulkan. But most importantly, they produce the SPIR-V spec. So SPIR-V, the history of SPIR-V, or SPIR rather, which stands for Standard Portable Intermediate Representation, in case you don't know. It was introduced as part of OpenCL 1.2. The first version of SPIR was 1.2, and it was heavily based on LLVM IR. So it was heavily influenced by LLVM IR. The reason why it was introduced is one of the issues of OpenCL, as some of you may know, is you package up the whole application and deliver it to the user, and at runtime, the compiler will compile the kernel code to execute on the GPU. Some people felt that was a little bit of a restriction in that they had to essentially give away an awful lot of their source code for someone to read and get inspiration from. So the main purpose of SPIR was actually to obfuscate that process a little bit. So you had to go through a decompilation step to get back to the original OpenCL. Moving forward 3 years, OpenCL 2.0 was released. So there's a new version of SPIR was released. Again, it was very closely matched to LLVM IR, just a newer version. And again, move forward an extra year, and the GL Next effort within Chronos, which was to define a brand new graphics API, produced Vulkan. Now this had some of the same issues that OpenCL had. It didn't necessarily want to have your shaders given away for free to people, but also they wanted to reduce some of the compilation complexity from the runtimes. So the objective of Vulkan is to be really cut down bare metal API that really sort of extracts the maximum performance out of the GPU. And it was viewed that SPIR-V would allow some of the compilation effort to happen up front, so it's not happening at runtime all the time, but also produce a very simple layer which every shader language could build on top of. One of the criticisms of GL was always that the shaders, even though they're a standard, every vendor would compile them totally differently. So you'd have totally different issues and different bugs. So SPIR-V is an attempt to just create a common sublayer which everyone can target, making it quite simple. And the latest version of SPIR-V 1.1, released last year, is to support OpenCL's C++ kernel language. So OpenCL with 2.1 introduced it as an extension to have a C++ kernel language alongside the API. So I've touched on it slightly, but what's the purpose of SPIR-V? So it's an intermediate language which all the different APIs within Chronos can target. So rather than having SPIR and something different for Vulkan, which would just confuse things, Chronos decided to have a single API, a single low-level language, which would sit across and underneath Vulkan and OpenCL. So that its main purpose is to accurately represent the semantics of both of those APIs. So everything that you can do in a higher level GLES-like language or GLSL-like language, you can represent directly in SPIR-V. It's not designed to be coded by hand, and I'm sure when I show you some examples, you'll understand why, but in the same way that LLVM IR is quite complicated and difficult to understand sometimes, SPIR-V is the same thing. Yeah, and as mentioned, the requiring a decoding step to uncover the algorithm was seen as an extra protection against people copying your novel algorithms. So very much SPIR-V is designed to sit as an intermediate layer for a lot of different languages. So obviously you have HLSL here, but the point is that a driver, a GPU driver, can just consume SPIR-V by itself. It doesn't have to support all of these languages at the top, and there may very well be other languages, shading languages that people want to invent in the future, which could introduce all sorts of interesting features which we haven't thought of in Chronos. But the point is, as long as it can target SPIR-V, then they'll have an avenue for executing on the GPU. So all of these tools here can be, to produce SPIR-V, can be open source. And there are quite a few open source tools, which Jakub will go through in a little while, describing how to get from things like GLSL, Vulkan GLSL, and OpenCL down to SPIR-V. There are also a whole bunch of open source tools to do with optimizing the SPIR-V that gets generated from some of the standard tools. Again, this is going to be a target-independent optimization, so it's not specific to a particular GPU architecture, but it's just a general optimization, as you can imagine, from high-level optimizations in LLVM. While it's not designed to be assembled and disassembled, it's not supposed to be used in that way, there are obviously tools to produce a text-readable format for people to understand what's going on. And the other key thing, or interesting thing about this, is it introduces validation tools. So as I describe the SPIR-V components later on, you'll understand that actually validating the SPIR-V means that you can be confident that when you deliver your SPIR-V shader to a GPU, as long as that GPU is conformant to the spec, that it will execute. And this gives you an extra little validation. So the main purpose of this, an awful lot of complaint about GL is that an awful lot of effort is taken in checking results of API calls. So Vulkan introduced a validation layer so that when you ship your algorithm, you can remove all the error checking, but you know that while you're developing the algorithm, not all the error checking is in place. And the validation layer and the validation tools for SPIR-V kind of provide that assurance that when you actually release the application, you can remove a lot of the error checking because you know that it's correct. So finally, we come to the GPU vendor, and really all they need to do is obviously implement a GPU, which is pretty easy, but take the SPIR-V and produce the binary which runs on their particular GPU. So it takes an awful lot of the higher level optimizations and work out of the task, and obviously allows, as I've mentioned, a common interface for shading languages to all of these GPUs. So I'll now briefly go through the SPIR-V structure. It's quite complicated, and I'll probably go quite quickly, but as I said, if you've got any questions, just catch me at the end. This is a GLSL shader, relatively straightforward. It's just taking in, based on some input conditions, do a calculation to set the color output from the fragment shader, and then just doing a little loop which multiplies it. So pretty straightforward and simple fragment shader. I'm sure you can all read that. But that's the SPIR-V that gets produced at the end. So as you can see, there's quite a lot of complexity there, but I'll go through each section and we can describe it. So at the top of a SPIR-V shader, the first thing you'll see is a set of capabilities. So the first thing you do in your SPIR-V code is you specify what is my shader or kernel going to execute, what features of SPIR-V is it going to use. So here we're saying that it's declaring that it's a shader, it's a shader capability, and then a bunch of other capabilities underneath, which is saying I'm going to use 64-bit ints and half float values. And the validation tools will read this and read the rest of the code and make sure that you haven't used something which is invalid. And obviously, if the GPU equally doesn't support these capabilities, then you'll get an error when you attempt to execute it. The next thing is the memory model and addressing model are specified directly, which is a little bit different than LLVM. So here we're saying that we're using GLSL. We're specifying the logical memory model, logical addressing model, which means that pointers are abstract. You can't create an op variable of a pointer, and therefore pointers to pointers are not allowed. The other options for that are non-logical addressing model, which again allows physical pointers to be created. So for example, for OpenCL, you would use that. And you can have both physical or 632 or physical 64 memory model, addressing models. So the memory model, again, is specified directly as part of this instruction. So the other options here are simple, which gives you no sort of consistency semantics, or the OpenCL 2.0 memory model, this should say, which obviously defines all the features of that model. So this, again, is different than LLVM IR in that you're specifying these things directly. The other thing that's different from LLVM IR is that you specify the entry points as an instruction in SPIR-V itself. So again, here we're specifying a fragment. We're saying that the main function is the entry point to this fragment shader, and it's also specifying some extra information about the execution mode. So a good example of an execution mode, for instance, would be you can specify the local size for the kernel invocation, and this could allow some extra level of optimization when you're compiling this shader, if you know the local size, then you can maybe make some extra improvements to the generated code. So what are some differences between LLVM and SPIR-V? And I suppose this is maybe the main thrust of my talk today, is how can we make LLVM support SPIR-V-like concepts to allow LLVM to more accurately represent some of these concepts that are important for certainly for graphics, but also for OpenCL. So Vulkan shaders, you have to have structured control flow. For OpenCL, you only really need reducible control flow, but for Vulkan shaders, you need to have merge blocks. So one of the instructions within SPIR-V is op loop merge and op selection merge. So as part of the loop header, you specify basically which block is going to come back from your back edge and where is the merge block, so that once the loop's finished executing, it knows it's going to hit that point. And one of the issues is that some LLVM optimizations can introduce changes to the code that result in certainly unstructured or possibly irreducible control flow. And just one of the examples, I'm sure you've all seen this one before, one of the examples of an irreducible control flow problem is Duff's device. So this would be difficult to implement in Vulkan. So if your LLVM compiler ends up producing something similar to this, then you're going to have undefined behavior on OpenCL and certainly on OpenCL, but also on Vulkan. So this is another key difference, is an awful lot of the semantics of OpenCL is represented by metadata. So if we have a relatively straightforward OpenCL kernel running through the LLVM tools, client front end, we produce all of this metadata, which gives extra information about, this is sort of the entry point of the kernel, and you've got to parse all this extra metadata here to find out which the arguments are, so one of the issues is, in order to work out what's happening, you have to parse this metadata often. Whereas with SPIR-V, as I've already mentioned, all these things are kind of explicitly stated in the instructions. So you have entry points, kernels, specifying what source it is, specifying all the different function input arguments, global arguments, and function arguments. And from our point of view, it's a nice feature to have it actually part of the language itself, rather than relying on this metadata, because as things go forward, more complicated semantics are implemented into OpenCL, we don't want to keep relying on this metadata. It's not as much of a problem for OpenCL, I suppose, but certainly for LLVM, it does have, sorry, not LLVM, so Vulkan, it has some extra complexity. So there are some things that really can't be represented very well for Vulkan, and I'll get onto some of those issues in a moment. So another one is, uniform control flow. So SPIR-V has native opcodes for barrier operations, cross workgroup operations, and LLVM doesn't really have that kind of concept. It's just viewed as a single thread of execution. So LLVM has to introduce extra features, basically. So one of those ones is the convergent function attribute. So for a texturing operation, you could have, it'll be a built-in function call or an intrinsic to do your texturing operation for Vulkan, with the convergent function attribute, which essentially means that what you're telling the code generator is that don't reorder instructions around this barrier, essentially, because it has some extra semantics which isn't clearly represented in the LLVM as just a function call. So you need to capture that in some way, whereas SPIR-V captures that directly in the instruction. You understand when you specify an op barrier or a particular op texture operation, the semantics of that are, it's going to be, certainly for derivatives, for example, the semantics of that are going to be that it's going to be operating across a group of threads at the same time. So SPIR-V directly captures that in the LLVM IR itself. The other difference is, you have fully composable types. So what do I mean by that? So this is an example of a simple struct containing two elements. And this is the SPIR-V, which first specifies, that should actually be a 1. But this first specifies this is an int. This is just specifying the constant 3 here for the array, which is this constant. And then you're building up that you then have a vector, which is a different vector type. And then you have a different type float, and then you have a float of vectors, which takes the constant as its element. And then finally, you have this struct built up of these different objects. So the type system within SPIR-V sort of builds up in complexity as you go along, and you can reuse types in different scenarios. Okay, so that's a quick lightning introduction to SPIR-V. I'm now going to pass over to Jakub to present a little bit of information around the tooling.
Okay, so when it comes to tooling, there are three main projects. Two of them are mostly maintained by Google, and those are SPIRV tools and GL Slang. SPIRV tools are heavily resemble LLVM infrastructure. There's assembler, disassembler, optimizer, and validator that Neil briefly mentioned before. Assembler and disassembler can turn between textual and binary representation of SPIR-V. Because even though it was not designed to be modified by hand, it is still useful when you are developing some tools to just modify SPIR-V and go between binary and textual representations. Validator is also very useful because sometimes you are building some tool and when you push your binary on your device, you run it and it runs fine, but it can still be ill-formed and it can also crash on some other devices. GL Slang is a reference shader compiler made by Chronos, and it essentially is a front-end and code generator for graphics and compute shaders. It also supports binary and textual representations, and it also provides this neat tool called SPIR-V remap that takes a bunch of different SPIR-V modules and makes them more similar by naming certain values so that are similar to each other across different modules. Say you have defined two floats in different modules, but they ended up having some different names because of some reasons. And it's just really inconvenient for a float to be named something like %13. So that's helpful. When it comes to the optimizer, it's currently very sophisticated. So it can, for instance, strip debug info, which speeds the execution a lot, as you can imagine. It also can false constants, and it basically is, yeah, it doesn't do much at the moment. But I see that it can be useful in the future if they decide to implement some optimizations into the optimizer. There's also this tool called SPIRV LLVM, which converts between SPIR-V and LLVM. So it is advertised as like a lossless round-trip conversion, and it's mainly used by the OpenCL Clang-based compiler. So it lives inside the LLVM tree, and it's like basically a library inside of the LLVM itself. But because of that, it's a forked tree, and it lives downstream somewhere on the Chronos GitHub repository. And it's based on some old LLVM version, and the newer one doesn't really work well and doesn't even pass most of its tests. Maybe not most, but there are some failing tests for months there. And here's a simple example of like a hello world in OpenCL, which just takes two arrays, multiplies corresponding elements of those arrays together, and stores it in a third array. And when you compile it to LLVM, it looks like that, and it has a lot of attributes and such. And when you compile it to SPIR-V, it gets longer, but it's cleaner, perhaps simpler. And you can use this tool to do this conversion, and you can actually use this tool to do the back conversion. But when you go back, you lose some of the information, such as attributes and flags on some operations, like no unsigned wrap or no unsigned wrap. And as I said, most of the attributes are gone at this point. When it comes to the SPIR-V community, there is a public GitHub group called Chronos, and it has many repositories, not only about SPIR-V itself, but also some other tools. There are some public forums, which you can look up online, but there's really not much happening there. Like, there's virtually no discussion there, and all of that, in my opinion, is pretty stale. You can also pay to be a member of this Khronos Group, which is a bit pricey, and it gives you access to some internal forums, and you can also participate in some conference calls that happen regularly each week. But still, the environment feels a bit fragmented, and it's not very transparent. There's not much development happening really openly to the public. One of the examples of some inconsistencies in the SPIR-V ecosystem are textual representations. So there is one that is used by GLSL shader language. Then there is other one used by SPIR-V LLVM. So there's a difference there. And there's a third one used by SPIR-V tools. It's obviously the best one because it offers some nice coloring, which is very helpful. Other than that, this is the only textual representation that is actually usable with both compute and shader SPIR-V code. The other ones are specific to shaders or OpenCL only. Other than that, there are also 5 different in-memory representations that I know of. Yeah. When it comes to compute, there is also a little split in that, because there's like a separate substandard for compute shaders and kernel code for OpenCL. And there are different extended instruction sets that are available to both standards. So there's like a common part in between those, but it's not explicit, and there's some duplication to it. And it also varies in the way with dealing memory. Say, there are different ways of passing arguments that are available to each format. And when you are developing a new compiler, a new tool, you have to somewhat decide whether you want to target compute world, meaning compute shaders, or you want to target OpenCL. And making an OpenCL driver is a lot of commitment, and it's very expensive in terms of the work that you have to put into it. And SPIR-V has also some limitations. SPIR-V has no ways of expressing function pointers. There's just no function pointers in the language itself. As Neil said, there is also a problem with non-reducible control flow, and recursion is representable, meaning you can have recursion in your code, but it can just fail during backend compilation. So you compile it to SPIR-V, you run it on your device, and it crashes. Same happens when you try to do some deep call chains, say like 4 or 5 levels on some targets. So you have something like main. In main you have foo calls bar, and when you go from bar to something else, it can just crash. Okay, so there's summary now, Neil?
So, Jakub made it sound like SPIR-V was broken in some way, but I mean, the point is that it's designed for the class of architecture that it's going to execute on. So obviously it's designed to run for Vulkan, and it's designed to run for OpenCL. So some of these issues that you raise, function pointers, are not relevant in that space, so it's not been implemented. But it is an active area of development, so as OpenCL is extended, as Vulkan is extended, hopefully maybe at some point in the future Vulkan Compute becomes more similar to OpenCL or well-rounded, then some of these problems, as Jakub mentioned, should hopefully be solved. I did mention earlier one of the issues of LLVM, which I said I would come to later on and then didn't, so apologies for that. But for instance, one example in Vulkan, which is difficult to represent in LLVM, is Vulkan, or Vulkan for GLSL anyway, has different structure packing mechanisms. So stud 140, stud 430, which sort of represent how matrices and vectors of matrices are represented in the structure. That's one of the issues that the LLVM can't really represent very, very well. And obviously one of the ways of doing that is to, again, misuse, however you want to put it, the metadata feature of LLVM. So, I mean, what we want to see, or what we'd like to drive towards as a community, as the LLVM community, is how can we essentially extend LLVM in some way as a standards, as a group of us, to represent some of these concepts in SPIR-V more accurately, more cleanly, really. without the need to rely on this metadata hack. So that's really what we want to get out of this. Jakub briefly mentioned SPIRV LLVM converter. That's something that we, the LLVM community considered taking into tip of tree, but we'd like to maybe revisit that discussion, see how to integrate some kind of translation from SPIR-V to LLVM. We're probably going to have to implement a backend for SPIR-V realistically, but also how we take SPIR-V in as a front-end language. How do we add that into the LLVM body of work, as it were? And equally, I think it would be good for LLVM to try and extend it, to encapsulate some of these more diverse hardware targets. If we have GPUs running, CPUs running, or using LLVM, I think that's a good thing for us as the LLVM community to get that working. So we are planning to have a hacker event tomorrow. If you want to come and talk to us about SPIR-V in LLVM or any other issues regarding GPU execution, or OpenCL or some other things, then please come along to one of them. It should be on your agenda. I can't remember the time, unfortunately, off the top of my head, but it'll be on your agenda. And yeah, I think that's all. So thank you very much for your time.
Yeah, thank you for your report. I saw that you have a tool that converts SPIR-V to LLVM and back, right?
Yeah.
And is the code the same if you convert it?
No, I mean, I think that's what Jakub said. It's an active, it's under active development. Well, it's under development, let's put it that way. So there are some things which get a little bit mangled differently.
Okay. So we lose some context, right?
We lose a little bit of maybe representation or semantics. I'm not exactly sure what this one is showing, but there are some cases where you do lose some information. But again, it's not an official tool. It's something that's being extended. It's something that's being worked on to make sure that you don't lose that information.
Okay.
Essentially, so there are some slight differences.
Right. Can I do you first? Just as path optimization.
Yeah, you mentioned Optimizer tool that worked on the SPIR-V representation. I just wondered, is there any advantages to doing optimizations on SPIR-V versus LLVM IR? Do you have any more information that helps you, or is it kind of...
So one of the points is that the SPIR-V is meant to be portable, so that you have some code, you have some language of your choice, you compile it to SPIR-V, and then you distribute the SPIR-V modules across devices. And then the driver on the device does final compilation. So that in this way you can, the optimizations that you can do on the SPIR-V are somewhat limited because you don't know the final target. So what happens in practice is that some drivers take the SPIR-V, convert it back to LLVM, and then optimize.
So GL slang is completely open source, if I understood you correctly?
Yes, it's available on GitHub.
Okay, and so what this sounds like is that the Khronos community, consortium, whatever, tries to encourage people to build backend, say, for SPIR-V, however you pronounce that? Is that what's...
Yeah, so I think that's a bit of a difference from how Khronos has operated in the past. I think Khronos has traditionally been quite a closed standards body in the sense that it's not taken an awful lot of input from the community, and that's certainly changing with Vulkan, but with SPIR-V as well. Is Khronos want to engage with us, the community as wider, and hopefully get input from the wider community on how to improve these things. So both GLSL is open source. The SPIR-V to LLVM converter is also open source.
And based on all these issues that you've sort of mentioned, with these different standards and different different like code that's produced, like if you sort of like follow different code generation paths. Can you comment on your experience with GL slang? I mean, if you just like use GL slang and combine it with your SPIR-V backend, does that work? Because from what I've seen, it sounds like there might be some issues. And if it works, can you comment on whether that produces sort of like satisfiable performance in the front end?
I think maybe that's been slightly miscommunicated. So what we're touching on here is that the interaction between SPIR-V and LLVM isn't robust. The SPIR-V itself is very robust. So the specification, GL slang is a very good compiler. It's kind of the reference compiler from Chronos. So as long as your driver that you eventually run the SPIR-V on is conformant driver, then it will execute fine. So there's no issue from that point of view. And also there are many drivers released for Vulkan, and there are games running on Vulkan, and similarly it supports OpenCL. It's just what we're bringing here is the interaction between SPIR-V and LLVM, and the issues around that, rather than that there's anything wrong with SPIR-V. SPIR-V, you know, it's a standard, it's well supported.
Other than that, there's also this issue that SPIR-V is well standardized, whereas tools are quite new, and they maybe now and they are not like 100% robust, and there are some inconsistencies. But in the long run, they will definitely improve.
You talked about portability. Can you say a little bit about what hardware, what devices you have backends for, how well they perform, partly, especially because, at least in our experience, getting performance on different GPUs can be really hard. And I'm just curious what your experience is.
Sure. That's a really good question. So I guess the main focus of Vulkan is not to try and be performance portable, but it's to try to expose enough of the underlying hardware to you via API calls or via other information that you can interrogate at runtime from the device, that you can write a performant implementation on any architecture, but it's not necessarily going to perform the same way across different architectures. So what you're certainly seeing with Vulkan is certainly some of the big game engines or optimizing with different paths for different GPUs. And I think one of the issues for GPUs, as you pointed out, is that they're all very different, and actually getting performance portability across GPUs is incredibly hard, and maybe isn't really what we should be focusing on, because you end up compiling to the lowest common denominator in a sense. What Vulkan is trying to do, and I'm sure maybe OpenCL as it develops into the future, is to actually give the developer all the information that they require to write for the particular GPU. Now that of course has implications for people, you know, writing middleware or whatever, that you have to optimize for different paths. But that's kind of the direction that Vulkan's certainly taken, is to expose all that information to the developer directly.
So if I can just follow up on that, I think part of the reason you get that is if you have a low-level representation. As you said, I think SPIR-V is even lower level than SPIR used to be. That makes it even harder to make the code performance portable. If you had, it seems to me, if you had a higher level layer of abstraction in the code representation, you could do much better in terms of performance portability and do more aggressive optimizations in the code generators.
Yeah, that's possibly true. I mean, I think the issue with that is that certainly with compiling to SPIR-V, if it would have to be an external tool, then you would have to know what your target was going to be in order to optimize for that particular architecture, if you see what I mean. So, I guess it is a problem, and it's probably going to result in people having slightly different versions of SPIR-V for different GPUs, and it's not ideal from that point of view, but really the focus is to expose as much of the underlying GPU as is possible to a developer. So I agree with you, it's an issue, but if you have any ideas of how we can solve that, then, you know, that'd be great, yeah.
Right, any other questions? Right, then if not, let's thank the speakers again.